So, it is very important to know theory of probability to know the postulates of statistical mechanics. If you do not know theory of probability, you do not appreciate the theory of probability, you will not be able to appreciate the beautiful postulates of statistical mechanics that go into it. Without going into details, let me tell you, there are whole statistical mechanics is based on, and I'll elaborate on my comment that why what I meant this probability theory and thing. Many of the things I have to as I talk they will come to me, and the way it happens to always a teacher. Now there are two postulates and one hypothesis. And just like whole quantum mechanics follows from Schrodinger equation, you know, is still stands as a hypothesis. The two postulates and one hypothesis is the total cornerstone of statistical mechanics. Everything of statistical mechanics, and by extension our understanding of thermodynamics of natural phenomena, everything from these two postulates, and we need a hypothesis, and that I will explain why I need the hypothesis. Now what are the two postulates? Okay. The two postulates, in order to understand those two postulates, we would need to know few other things, but let me tell you the two postulates, then I will go back and forth because they are very important. Then I will see to understand these two postulates we need to know some things. Okay. The first postulate is what Gibbs introduced, time average equal to ensemble average. Okay, time average is like that, a quantity x time average. The way you do, you take a long trajectory. As I tell you, I need to talk of trajectory. I am observing a system for a huge long time. Then time average is that I am just taking one random variable. I am not talking of correlation. That has a little bit more complex, and I am not going to do immediately that. So I take snapshots. I measure the values at different maybe equal time intervals. Then I say limit t going to infinity, and this is time 1 over t 0 to t ds xs. This is the time average. Is this clear to everybody? This is a very important thing, this time average. That what we are doing, we are measuring the time, it is fluctuating as we discussed, it is fluctuating, but I have this time. Then I say okay, I do it up to time, a long time t, then I take the time t going to infinity, and I do that, and that becomes independent of t, and this is the time average. Ensemble average is the one that Gibbs introduced, that you have a mental replica, billions of billions. So instead of time average, now I construct, and this was the, you know, whenever it helps to be very relaxed. So you have this glass of water, identical, many same amount of volume, same glass, same water, everything, billions of time. Now instantaneous configuration of water in one of my, say these are my mental replica, this is my original one. Now the mental replica controls its volume, its density, its temperature, say, or volume, total number of water molecules, and its energy if they are in isolation, NVE. But other than that, it does not control what are the positions and orientation of the water molecules. So each of my mental replica position and orientation of the water molecules are different. This is very important. So, I am constructing, it is a brilliant construction done by Willard Gibbs. He created a mental replica and he realized that if they are identical in macroscopic sense, NVE, I have no control over his microscopic, and there is a huge number of microscopic states. They are something like, you can say 10 to the power n or a to the power n, exponentially grows exponentially number of particles. So, each of them are distinct microscopically, very important to understand that. They are exact macroscopically, but they are distinct microscopically. So, now I can go and say, okay, they are macroscopically identical, but they are at the same time, an individual of them will have a little different value of the x, but now I can average over them. That average will be by this, always by the angular brackets, that limit n going to n is my mental replica, then 1 over n sum over the values. This is my ensemble average. Again, ensemble is a mental construction with the condition that macroscopically they are the same, microscopic they are distinct, because a microscopic system has huge number of microscopic states. And now I go in my mind, I calculate the by the x for each of my system, and as I said, n is billions and billions and sum over then the first postulate of statistical mechanics is time average equal to ensemble average. That is the first postulate of statistical mechanics. Now, we will do the second postulate. Now, anybody knows the second postulate? This is really a beauty. Huh? Exactly, equal a priori probability. Now, tell me, since you have told me, what is it? Exactly. So, but at the core of that, all my systems are NVE, and each of the microscopic states are equally probable. Why did you need that? Okay. One thing I did not, so this number 2, number 1 I go back little, when I did do this thing, I limit n going to infinity, strict sense I have to do pi xi. N is the my system, number of system. So, if they are equally probability, 1 over n comes here. So, that is the reason. So, Gibbs had no other option. You know, he wrote this pi xi, but he had no other option, but he was working in NVE. He knew Boltzmann distribution, that is same energy. The only sensible thing is to do is to equal a priori probability. This is really beauty. So, now we have done the two postulates. Okay. I will go through little bit more detail on my notes because of the trajectory and phase space and all these things. Now, I have done the two postulates of statistical mechanics, time average equal ensemble average and equal a priori probability. So, you now realize the first postulate required the second postulate, without that we do not go anywhere. Now, Gibbs needed, that is of course this thing is given to Boltzmann, the ergodic hypothesis, because Boltzmann used it earlier. Now, now anybody can tell me what is the ergodic hypothesis, and also tell me, or others I will tell you why we need the ergodic hypothesis. This is really very, very impressive. really very intellectually stimulating so we had two hypotheses. I said the whole statistical mechanics is based on two postulates and one hypothesis, that is all. Everything follows from that. The huge construction, huge theoretical framework of statistical mechanics which everybody uses, whether biology, chemistry, material science, physics, that is the theory of many body systems. There is no other, but the whole thing is based on two postulates and one hypothesis, and the name of the hypothesis is Ergodic Hypothesis. But why do we need the Ergodic Hypothesis, and what is Ergodic Hypothesis? Tell me.
Isn't the first postulate the statement of the Ergodic Hypothesis?
No. So what is now? He tells me it is not enough to have equal probability, but the particle system must go from one to the other. System must not remain trapped in one state. So Ergodic Hypothesis now tells that the system visits every state. That is why glass, we have the problem, breakdown of ergodicity. So the second hypothesis guarantees, forces the system to go through all those states. Being equally probable is not enough. If there is a large barrier between them, you do not go from one state to other.
No, I mean first the time average.
No, because I cannot put ensemble average equal to time average if I do not have equilibrium probability. Once I have equilibrium probability, now if my frequency is like that, it does not go from one to here, it gets stuck here. That is the computer simulation all the time, you break down ergodicity. So we need it to go, and that is why you need the Ergodic Hypothesis. Okay, now I will go through some things. So we have two postulates we have done. Now I have to do, I would like to tell you about the concept of phase space. I would like to tell you about the concept of trajectory, because without trajectory we do not have Ergodic Hypothesis or equilibrium probability. Without phase space is a sample space, we do not have the probability distribution. So these are the two things that I need to do now. Let us consider a single atom and and start following its position and velocity from time t equal to 0. So in order to get all its future thing in the position and momentum space, we need two coordinates. In a one dimension we just need two coordinates, one is position and its velocity. They can be plotted against each other. So the way one plots this phase space is the very initial is of the classical mechanics, but this is the way classical mechanics is usually not taught. Okay. So if it is x and is momentum p, then this is the kind of thing that you get, the particle moving through with the different velocity and different position, and this is called the phase space. So the p and q or p and x, this is the phase space of one single particle. In 3 dimension, this phase space of a single particle will be 6 dimensional. Okay. Sometimes it is called mu space. Now it is very important that so now we are trying to understand the trajectory and quantify the trajectory and the phase space. The location of the particle in the phase space. So this space which is defined by position and momentum is called the phase space. So this gives, so the phase space gives you the movement of a system. If I have a one particle only, then it is sometimes called mu space, and one particle in 3 dimension is 6 dimensional space. So phase space of a single particle in 3 dimension is 6 dimensional, and in 2 dimensional the phase space is 4 dimensional. However, in our world where interacting system, we have a n dimensional, a n particle system. So n particle system, then we have a 6n dimensional space. This is something which puts of students, but it need not really be difficult. So, the phase space is of n dimension, n particle is 6n dimension. However, you are not going to really work with it. In one of the major thing of statistical mechanics is that you have to go through the formalism, understand the formalism. So, this is required to derive the equations, and one thing of stat mech, this is from beginning to the end, it is a highly mathematical subject. This is one of the reasons probably in chemistry it is not taught that much, but unfortunately for all of us, without stat mech we cannot do anything, we cannot do any of these studies, theoretical understanding. So, but this mathematical grinding that we go through, or mathematical kind of conveyor belt that you go through, is not terribly difficult, and at the end of that you have equation which is tractable. Okay. So, right now so the phase space is a 6n dimensional system of which 3n, okay, this phase space of n atoms, I have not gone to molecule yet, n atoms, and that is 6n dimensional, 3n coordinate plus 3n velocity or momentum. Now, as I am considering a system, n number system, n number of particles here, then I draw the phase space now, vector n, that means this is 3n and position q n. This is the 6n dimensional phase space. Okay. This is 3n dimensional, I cannot draw 6n dimensional, so I have drawn it 2 dimensional. But this is 3n, this is 3n. Now I have n number of atoms and molecules here, which are undergoing collisions, which are moving in a solid, they will be vibrating, liquid they are colliding and changing positions. So, instantaneous state of my system is a point in this thing, because a point has 6n values, and then that determines position and velocity of each of the particles. Is a reduction in description, but it is still hidden, nothing has been solved, but we are developing a formalism. So, now as the system moving, this particle going here, this is going there, this is going here, this is coming here, all these things, as the particle is moving and my system going from one microscopic state to another microscopic state, I am here moving in my phase space, okay, because this gives my starting position, next position this, each point is important thing, each point signifies instantaneous state of the system, okay. This thing, so the 6n dimensional phase space, so the motion of the system in this phase space is called the trajectory. So, in computer simulations, when you are doing averaging your trajectory, you are actually following through all your 1000 particles, say atoms just, then you have taking care of this 6000. At any given time, you are going time t to delta t plus delta t, you are doing little bit here. Yes. All the particles have the same momentum, they will move in one direction. If all of them have the same direction, then there will be translational movement, right. All of you I give the same momentum in that direction. So, you will just move in that direction, okay.
Because whose time the movement
Yeah, that is very easy. You will have a whole system will move. So, this moment, the position, this one will move with the same velocity. So, it will parallel to P and it will move in Q direction with a constant velocity.
So the P, you can just extract from the Q. So if you know the Q, the position. So change of the position will be the velocity.
Absolutely. That is what, you know, the equation that gives you the motion in the phase space is nothing but Hamilton's equation that we write as a Liouville equation. So, Hamilton's equation gives exactly that quantity. Okay. Now, it is a very good question because it brings to the essence of classical mechanics and movement of the particles in the phase space. Now, so one particle system we can do that. So, now we have understood the, let us get a few examples. So, let us take an harmonic oscillator of a single one particle harmonic oscillator, then depending on energy, now it is a bound state. Bound state means it will be like this and is an ellipse because this is an ellipse. So, phase space is now highly restrictive. If you talk of vibrational energy relaxation with the discrete energies, then you will be going from one state to another state and you know some very interesting things happen. Okay. Free particle, however, is not a bound state, it can go all over the phase space. So, this is a free particle, one free particle that is moving. So, harmonic oscillator, bound state, this is a free particle, then two particles are trajectory. Now, I want to consider trajectories of two particles and then they will be, I will be of this we do all the time in computer simulations. Really interesting this trajectory, say we are doing a chemical reaction and chemical reaction is from going from one bound state to another bound state or one quasi bound state to another quasi bound state. Then you get this guy is going around moving here in a bound state character is always like that, okay. So, then it is going like that, then it escapes the barrier, then goes to another bound state. So, character of the trajectory in the phase space tells a lot of what is going on in the system.